everyone! Welcome to part 1 of chapter 11. This chapter is all about using information from balanced chemical equations to do lab-based calculations. Today, we are going to get an introduction to stoichiometry, which is a key calculation in all levels of chemistry. This is one of my favorite chapters because it has a lot of practical applications for lab, which I think is the best part of chemistry. So let's go ahead and get going. So we've already learned about the law of conservation of matter. The law of conservation of matter told us that matter cannot be created or destroyed, and that's why we needed to balance chemical equations so that the same number of, let's say, oxygen atoms ends up on both sides of our chemical equation. So we're not destroying oxygen, we're not creating oxygen, right? Just everything that we started with ends up in our products. The law of conservation of mass is very, very similar, but instead of counting the number of oxygen atoms or aluminum atoms, now we're basing it on mass. So the law of conservation of mass, which we usually measure in grams, states that in an ordinary chemical reaction, matter cannot be created or destroyed, therefore there is no change in the total mass during the reaction. So essentially the way that this breaks down is that the mass of the products is going to equal the mass of the reactants. Because if we have the same number of carbon and oxygen and hydrogen atoms in the reactants and the products, then that means the mass is the same as well. So the law of conservation of matter and the law of conservation of mass go hand in hand. But when we're talking in this chapter about weighing things in grams, it's more useful to think about it in terms of mass than it is in terms of individual oxygen atoms. But it kind of plays out the same way. So the law of conservation of mass states that the total mass of substances in a chemical reaction must remain constant. So everything that we start with, all of the mass of our reactants, must equal the mass of our products. So let's say we had 100 grams of water. We just kind of poured out 100 grams of water. If this underwent electrolysis and we were able to separate it into hydrogen and oxygen atoms, we would end up with 11.2 grams of hydrogen and 88.8 grams of oxygen for a total of 100 grams of our products. So we're starting with 100 grams of our reactants and we're ending with total 100 grams of our products. So this obeys the law of conservation of mass, because if we started with 100 grams, we have to end with 100 grams, right? Matter can't be created or destroyed, and so mass cannot be created or destroyed. All right, so let's review some topics we learned earlier in the course. Remember that the molar mass is the sum of the atomic masses of the atoms in an element or in a compound. So if we were to calculate the molar mass, we're just going to add up the masses of all of the elements in that molecule. We've been using this kind of as we've gone, so hopefully that has stayed fresh in your mind. We haven't used the mole in a little while, and the mole is better known as Avogadro's number, or 6.022 times 10 to the 23rd of whatever it is. So we usually said, okay, 1 mole of a substance contained 6.022 times 10 to the 23rd atoms of whatever it was. That was kind of how we most commonly used it. So we are going to use these as conversion factors in this chapter. You can think of chapter 11 as the return of the train tracks, right? These train tracks are coming back in full force. This is a math-based chapter, so just heads up, get your kind of train track mentality going on. So one of our conversion factors was that 1 mole of a substance is going to be equal to the molar mass of that substance in grams. Okay, so if this is 1 mole of an atom, then we're just going to use the mass on the periodic table. But if this is 1 mole of a compound, then we'll need to go through and actually calculate that molar mass. We can also use Avogadro's number as a conversion factor. Okay, Avogadro's number states that 1 mole of any substance is going to be equal to 6.022 times 10 to the 23rd units, whether it's atoms for individual elements or molecules if we have a compound. Okay, so we've learned those already, but those are going to be useful today as we move forward. All right, so today's lecture is an introduction to stoichiometry. Stoichiometry refers to the numerical relationship between the amounts of reactants and products in a balanced chemical equation. Okay, so what does that mean? Essentially, if we were to do this in lab, and let's say we weighed out some amount of our starting material, so some reactant. Let's say we weighed out 10 grams of whatever element A is, and I want to know how much of our product can be formed. So as you can imagine, this is really useful in chemistry. If I start with some amount of my reactants, I want to know how much of my product I can form. Because if I know how much of my product I can form, then the amount that I actually get when I do the experiment tells me how well the reaction went. Did I not get very much? Maybe I spilled some along the way. Or did I get too much and maybe that means it wasn't really dry, right? So being able to predict how much reactant or how much product we can make at the end of our reaction is really useful. Kind of like if we were to make a big batch of cookie dough, you might want to predict how many cookies you could make out of that cookie dough or out of however many chocolate chips. It's the same kind of thing. We're going to weigh out some amount of our starting material and we want to know how much product we can form. So that's kind of what we are working on today. So a key part of stoichiometry is a mole ratio. And the mole ratio is going to be found from the balanced chemical equation. Okay, really, really, really important that anytime you see a chemical equation in this chapter, and just in general in chemistry, you should always balance the chemical equation. Remember, we need to balance our chemical equations so that they obey the law of conservation of matter. And that is very important in chemistry. So here we have just a compound, a reaction of iron and sulfur to form iron 3 sulfide. Okay, you'll notice that 2 and the 3 in the front of iron and sulfur allow this to obey the law of conservation of matter. Okay, those are going to be key to our mole ratio. Essentially what this says is for every 2 iron atoms, I can make 1 of our product, 1 iron 3 sulfide. For every 3 sulfur atoms, I can make 1 mole of our product. Okay, so they're saying how many of each element it takes to make our product. So those numbers in the front are going to be the basis of our mole ratios. Okay, so again, in order to get those numbers in the front though, you need to balance the chemical equation. All right, so our mole ratio, technical definition, is a ratio or a conversion factor of the moles of any 2 substances in a chemical reaction. So you're always just going to relate 2 of our substances. So take, for example, this one. This is the formation of water from its elements. So we have 2 hydrogen plus oxygen gives us 2 water. So the coefficients in our balanced chemical equations are going to be used to generate mole ratios. Since these mole ratios are going to be used in train tracks, we are going to be thinking about them as fractions. Okay, I know nobody likes fractions, but remember, when things are equal, they get stacked when we do these train tracks, these dimensional analysis. So like for every 1 oxygen, we need 2 hydrogens. So that's what's showing here. For every 1 oxygen, we have 2 hydrogens. They're just using the coefficients from the balanced chemical equation to relate the amounts of 2 substances. Like if we were to relate hydrogen and water, for every 2 hydrogens, we get 2 waters, right? Or you could flip it upside down. You could put water on the top and you could put hydrogen on the bottom, right? And the placement of these is going to depend on how we need our units to cancel. Everything we've learned about train tracks still applies. Units are always going to have to cancel down and to the right. Just our one new conversion factor for today is going to be this mole ratio. And I think you'll find it's easier than it sounds. So our mole ratio can be used as a conversion factor, again, to convert between moles of one substance to another. So there's our equation that we were just looking at. And here's an example problem. This says if 4 moles of oxygen are present, how many moles of water could be formed? Okay, so just like any other train track, we're going to find out what we're starting with. Here, we're starting with 4 moles of oxygen. So that's what I'm going to put in the beginning of my train track, 4 moles of oxygen. You'll notice oxygen is O2 here, and that's because oxygen is diatomic. So anytime you see oxygen by itself, it's always going to be O2. Don't forget Hofbrinkel. All right, so making our train track, our units always have to cancel down and to the right. So since we have moles, we can use our mole ratio to convert between compounds. Okay, that's the whole point of the mole ratio, is it allows us to change compounds. Anytime we've done train tracks before with amounts of substances, we always stayed with the same substance. Like let's say we started with grams of water. We could turn that into moles of water or molecules of water, but it always had to be about water. Our mole ratio allows us to convert between water and hydrogen or water and oxygen. Right now we can change substances. So the way that we do that is through moles. Once you turn something into moles, now you can use our mole ratio. So we have moles of oxygen, on the top, right? So our units have to cancel down and to the right. So that means moles of oxygen needs to go down on the bottom. So we know it's going to say moles of oxygen, but we need to know what number. So our number we are going to get from our balanced chemical equation. Since there's no number here, that's an imaginary 1. So that's going to be 1 mole of oxygen on the bottom because we're getting 1 mole of oxygen in that balanced chemical equation. We're trying to find out how many moles of water. So moles of water is going to go on the top. And again, though, we need to know what number. So we are also going to get that number from the balanced chemical equation. That's going to be 2. So we'll put 2 moles of water on the top. So again, both of these we're just coming straight from that balanced chemical equation. And this step is called the mole ratio. Okay, once we have that, our units cancel just like they should, and we're left with moles of water, which is what we are trying to find. Then we can multiply all the numbers on the top and divide by all the numbers on the bottom and get our answer. Just for significant figure purposes, this 2 and this 1 are exact. So the only one that's dictating our significant figures here is this number at the beginning. There's 2 fig sigs in 4.0 moles, so there's 2 sig figs in our answer. Notice here that we've changed substances. So we started with moles of oxygen and we're ending with moles of water. That's why it's very, very important to label our answer with the number, the unit, and the chemical, because now the chemical can change. Right? So it's not enough to just say 8 moles. You need to say 8 moles of what, right? And here we have 8 moles of water. So this is our answer. All right, let's try and do another one. This says, given the following balanced chemical equation, use the mole ratio to calculate 2 different problems below. If you're feeling confident and you think you can do this, go ahead and pause here and give it a go. If you're not feeling confident yet, that's okay. Just wait the couple seconds and then I'll go over it. Alrighty, let's give this a go. So this says the moles of water produced from 3 moles of carbon dioxide. Okay, so for part A, we are starting with 3 moles of carbon dioxide in the beginning of our train track. Okay, we'll set up our train track. Since we're in moles right now, we can use our mole ratio to change compounds, right? We're trying to find moles of water from moles of carbon dioxide, so we need to change compounds. So moles of carbon dioxide has to cancel moles of carbon dioxide down and to the right, and we get that number from the balanced chemical equation. If you'll notice, I was super nice and already balanced this chemical equation for you. Just always double check that it is balanced though. Sometimes I won't balance it and I won't say anything about it because I want you to recognize that you need to balance chemical equations. Right now though, this one's already balanced, so we'll go ahead and move forward. So our moles of carbon dioxide has to cancel moles of carbon dioxide down to the right. So moles of carbon dioxide is going to go down here. We get our number that goes in the front of that unit from the balanced chemical equation. Since there's no number here, that's an imaginary 1, so we're putting 1 mole of carbon dioxide on the bottom. We are trying to find moles of water here, so moles of water has to go on the top. Again, we're going to get our number from the balanced chemical equation, and that's going to be a 2. So we put 2 moles of water on the top here. Our units cancel, and we're left with moles of water, which is what we're trying to find. you'll notice that both of those numbers in that red box are coming from the balanced chemical equation. So that's the mole ratio, and that's what's allowing us to change compounds. Okay. All right, so once we've got our units canceled, we've found what we're trying to find, we can multiply the numbers on the top and divide by the numbers on the bottom, and we'll get our answer. All right, let's try part B. Part B is starting with 3 moles of water. So that's what's going to go in the beginning of my train track. Again, since we're in moles already, we can now use the mole ratio to change compounds. So we're trying to find moles of hydrogen. All right, so moles of water has to cancel moles of water down and to the right. So 2 moles of water will go on the bottom. And we're trying to find stuff about hydrogen, right? We're trying to find moles of hydrogen. So 4 moles of hydrogen will go on the top. Again, both of those numbers are coming from the balanced chemical equation. We're using that mole ratio to change compounds. So then we go ahead, we make sure our units cancel, and then we're left with moles of hydrogen, which is what we were trying to find. We'll multiply the numbers on the top, divide by the numbers on the bottom, and we'll get our answer. Alrighty, I want you to get some practice on this. Go ahead and pause here and complete problems number 1 through 5 on the Chapter 11 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so we've learned how to convert moles of something into moles of something else, and that's really helpful, right? That's using information from the balanced chemical equation. But if you think about how this applies to lab, weighing things out in moles isn't something we do, right? We don't like take our stuff and it tells you, oh, that's how many moles of sodium chloride you have, right? That's not how lab works. In lab, we weigh out grams of a substance, right? And then we use the molar mass to turn that grams into moles. Okay, so this kind of whole stoichiometry process actually gets a little bit longer because so far we've kind of been working on a middle step. What we really need to do is be able to start with grams of something and turn that into grams of something else, okay? And again, it's because chemistry is lab-based, and so we weigh things out in grams, not moles. So the way this is going to play out is we will start with our masses of our reactants rather than our amount of moles. So we're starting off with grams. And then we can turn that grams into moles using the molar mass. Once we have moles, then we can use the mole ratio to change between compounds, right? Our mole ratio, once we're in moles, allows us to convert moles of one thing into moles of something else. So when it says stoichiometric conversion factor here, that is the mole ratio, okay? And then once we convert it into moles of something else, we can use the molar mass of our product to turn it into grams, which we would also weigh. Okay, so we're making this whole process a bit longer, but it's because this is a practical application. We need to be able to weigh out grams of our reactant and grams of our product and be able to relate them to each other. So here's some key steps. The first one, like I've been saying, is to make sure our equation is balanced. If your equation's not balanced, you're going to do the whole problem wrong and you will be very sad about it. The next step is to convert whatever you're starting with into moles. So if you're starting with grams, convert that into moles. If you're starting with molecules or atoms, convert that into moles. We'll learn if you start with liters, you can also convert that into moles. So whatever you start with, convert it to moles, always. Once you convert it to moles, then you can use your mole ratio to change compounds. Okay? Remember, that mole ratio is coming from the balanced chemical equation, and that's going to allow us to convert moles of our starting material into moles of our product. And then, once you have moles of your product, then you can convert it out of moles into grams or atoms or molecules or liters or whatever it is, right? But the whole thing here is that you need to convert whatever you start with into moles, then use the mole ratio to change compounds, and then convert it out of moles. So here's what I like to call the Mole Island Diagram. And again, when in doubt, just convert it to moles. So whatever you're starting with, whether it's your mass in grams, your volume in liters, your number of particles like atoms or maybe molecules, right? It doesn't matter what you're starting with. Everything needs to get converted to moles. This mole island diagram is useful because it tells you how to do it. So like if you start with grams, you're going to use 1 mole equals the molar mass. If you start with particles, you're going to use 1 mole equals 6.022 times 10 to the 23rd. And we'll learn this one for volume a bit later. But once you have moles, then you can use the coefficients from the balanced chemical equation, which we like to call the mole ratio, to convert from moles of one thing into moles of the other. Okay? Once you've used the mole ratio and converted to moles, then you can convert it back out of moles. You can convert it to mass in grams, volume in liters, or, particles in terms of atoms or molecules, right? But the key here is that you always need to convert to moles so that you can use the mole ratio. All right, let's get some practice with this. This says what mass of hydrogen can be produced when 6 moles of aluminum reacts with hydrochloric acid. All right, so I've given you a balanced chemical equation there. You can notice that it's balanced because it already has coefficients. All right, so what are we starting with? We are starting with 6 moles of aluminum. So that's what goes in the beginning of our train track. So we'll make our train track here. Since we're already in moles, we don't need to convert anything to moles, right? Because we're already in moles. So that's great. That step is kind of like, check, done. We're already in moles. Once we're in moles, now we can change compounds using the balanced chemical equation. So now we can use the mole ratio to change compounds. Remember, moles of aluminum always has to cancel moles of aluminum down and to the right. So we'll get the number that goes with it from the balanced chemical equation. So that'll be 2 moles of aluminum that goes on the bottom. We're trying to find out information from hydrogen. It asks for the mass of hydrogen, but we can't go directly to mass. We can only use the mole ratio to convert to moles, just like it sounds. So we can convert to moles of hydrogen, and then we'll convert to grams of hydrogen. The important thing here is that we're trying to find out information about hydrogen, so right now it helps us to convert this into moles of hydrogen. So we'll use our moles of hydrogen on the top. That'll be 3 moles of hydrogen. Again, that whole step was called the mole ratio. So we'll make sure our units cancel, and now we're left with moles of hydrogen. We're left with moles of hydrogen, but we're trying to find out what mass, right? And mass is always measured in grams. So the way that we convert from moles to grams, and we've done this a bunch, is by using the molar mass. Okay, so the molar mass is 1 mole of hydrogen is equal to 2.016 grams of hydrogen. Okay, because there are 2. Remember, hydrogen is diatomic, so that's why it's called H2. So if we think about this conversion factor, 1 mole equals the molar mass. Remember, moles has to cancel down and to the right. So 1 mole of hydrogen will go on the bottom, and the molar mass will go on the top. Okay, then we'll make sure our units cancel and double check that we found what we were actually trying to find. So we were looking for our mass of hydrogen, and that's what we have. So then we can multiply all the numbers on the top, divide by the numbers on the bottom, and we'll get our answer. You'll notice that we only have 2 significant figures in our answer because we were limited by this. All right, so just to review, we started with moles of aluminum and we converted moles of aluminum into moles of hydrogen. We were able to do that from the beginning because we were already in moles. Once we found moles of hydrogen, we used the molar mass to convert moles of hydrogen into grams of hydrogen, just like we've done in previous chapters. Alrighty, let's go ahead and do another example problem. This one says, how many moles of water are produced when 325 grams of octane are burned? So we're starting with 325 grams of octane. You'll notice that my equation is already balanced, and thank goodness, it looks like quite a doozy. Alright, now that we have grams of octane, we are trying to get to moles of water. So at some point, we are trying to change compounds. We can't change compounds yet because right now we are in grams. The only way we can change compounds is to use the mole ratio. And to use the mole ratio, we have to be in exactly what it sounds like, moles, right? So our first step here is to convert grams into moles. Remember, anytime you're starting with something other than moles, your very first step is going to be to convert it to moles. So we're starting with grams, so we need to convert it to moles. So the way that we will do that is to do the molar mass. Okay, so whenever we're using the molar mass, we think about, okay, 1 mole of our octane is equal to the molar mass. And that molar mass is going to be in grams. So grams of octane has to cancel grams of octane down and to the right. So that means our molar mass of octane will go on the bottom and 1 mole of octane will go on the top to make sure that our units cancel. Once we've converted this into moles of octane, now we can change compounds using the balanced chemical equation. Okay? So when we change compounds, we need to still make sure our units cancel. Moles of octane has to cancel moles of octane. So that means 2 moles of octane are going to go on the bottom, and we're trying to find moles of water, so we have 18 moles of water that goes on the top. We'll make sure our units cancel, and you'll notice we were just trying to find moles of water, and that's what we have here. So we're actually done with this train track. Okay? Again, we'll multiply all the numbers on the top, divide by numbers on the bottom, and we'll get our answer. Okay, so looking at this problem was different from the previous one because in this one we were starting with grams, not moles. Since we were starting with grams, our first step had to be to convert grams into moles so that we could use the mole ratio to change compounds. We stopped where we did because this was just asking for moles of water, not grams of water. So we just used that mole ratio and we stopped. So just be really, really sure to read the problem carefully to figure out what you're starting with and what you're trying to find. All right, let's try this one. This says how many grams of silver nitrate are needed to produce 0.25 moles of silver sulfide. I want you to give this one a go. Okay, go ahead and pause here and see how far you can get. Once you're done, come back and I'll show you the answer. Alrighty, so in this problem, we're starting with 0.25 moles of silver sulfide. So that's going to go in the beginning of my train track. We are eventually trying to find out information about silver nitrate. So at some point, we are going to have to change compounds. I want you to always think to yourself, can I change compounds right now? And the answer here is yes. Since we're already in moles, we can go ahead and directly use the mole ratio to change compounds. So again, you always need to convert to moles, but now we're starting in moles, so we can just go ahead and use that mole ratio right now. So our moles of silver sulfide has to cancel down to the right with moles of silver sulfide. We only have 1 mole of silver sulfide in this balanced chemical equation, so that goes there. And we're trying to find out information about silver nitrate. So 2 moles of silver nitrate will go on the top because that's what's shown in the balanced chemical equation. Remember, that step is called the mole ratio, and the only reason we were able to use it right now is because we started with moles. We'll make sure our units cancel, and now we can go on with our problem. So right now we have moles of silver nitrate, but we need to find grams of silver nitrate. Anytime we're trying to convert from moles to grams or grams to moles, we're going to use 1 mole equals the molar mass. So if we're using 1 mole equals the molar mass in grams, moles of silver nitrate has to cancel moles of silver nitrate. So 1 mole of silver nitrate will go on the bottom, and our molar mass in grams will go on the top. Then we can make sure we found what we were looking for, right? We were looking for grams of silver nitrate, and that's what we've got. So now we can multiply all the numbers on the top and divide by the numbers on the bottom to get our answer. All right, here's another problem. This says how many grams of nitric acid are required to produce 8.75 grams of dinitrogen monoxide from the following reaction. Okay, so now you'll notice we're starting with grams and we're looking for grams. So this is actually a longer problem than we've done so far. But this is a very practical problem. This is a problem we would do in lab, right? We're going to start with 8.75 grams of dinitrogen monoxide, like if we went out and, weighed it on the balance, and I want to know how many grams of nitric acid I would need to have to make that amount, right? So again, because these are both grams, like I said, this is kind of a practical problem because we could actually weigh out these amounts in lab. But the way that we do it is exactly the same. So we start with 8.75 grams of dinitrogen monoxide. Eventually, we're trying to find out information about nitric acid. So since those are different compounds, at some point we are going to need to use the mole ratio to change compounds. We can't use the mole ratio right now because right now we have grams, not moles. So our first step here is to convert our grams into moles using the molar mass. Okay, remember we have 1 mole equals the molar mass in grams. Okay, so here grams of dinitrogen monoxide has to cancel grams of dinitrogen monoxide, so the molar mass will go on the bottom and 1 mole will go on the top. Make sure our units cancel so we can move forward. All right, once we've used the molar mass to turn grams into moles, now we can use the mole ratio to change compounds. Okay, so our mole ratio is always taken from the balanced chemical equation. So we have here is our dinitrogen monoxide. So there's only 1 mole of dinitrogen monoxide in our balanced chemical equation, and we would need 10 moles of nitric acid to make that amount of dinitrogen monoxide. Okay, so again, those numbers in this step are coming from the balanced chemical equation. We'll make sure our units cancel, and now we can go forward. So now we need to convert moles of nitric acid into grams of nitric acid. And the way that we do that is, again, using 1 mole equals the molar mass. So remember, moles has to cancel moles down and to the right. So now 1 mole of nitric acid will go on the bottom so that our units cancel, and the molar mass of nitric acid will go on the top. We'll make sure our units cancel, and then double check that we found what we were looking for. We were looking for grams of nitric acid, and that's what we found. So now we can multiply all the numbers on the top, divide by all the numbers on the bottom, and we'll get our answer. So this is a longer problem, right? Going from grams, grams of our starting material to grams of our product, but it's the same process. Whatever you're starting with, convert that to moles. Like here we started with grams, our first step was to convert it to moles. Once we have our substance in moles, then we can use the mole ratio to convert between substances. Then we can use the molar mass, or whatever it is, to turn that final substance into grams. All right, here's a practice problem. I want you to pause here and try this one out. This is a grams to grams problem, just like the one we did before. If you're a bit shaky on what we're doing, go ahead and use that problem as a model so you can kind of get the process. But if you can try it without looking at the previous problem, do that to kind of think through the process. All right, go ahead and pause here and try this out, and then come back when you're ready to see the answer. Alrighty, so in this one it says how many grams of chromic chloride are required to produce 75.0 grams of silver chloride using the following reaction. So again, this is a grams to grams conversion, or a mass to mass conversion. So let's go ahead and try this out. So we're starting with our 75.0 grams of silver chloride. Eventually, we're trying to find out information about chromic chloride, so we're going to have to change compounds. Since we're going to have to change compounds, we need to convert our grams of silver chloride into moles so that we can use our mole ratio. The way we convert to moles is we use 1 mole equals the molar mass in grams. Okay? Since grams of silver chloride has to cancel grams of silver chloride, that means our molar mass has to go on the bottom and 1 mole will go on the top. Make sure our units cancel and we can keep going. Once we have moles of silver chloride, now we can use our coefficients from the balanced chemical equation to convert moles of silver chloride into moles of chromic chloride. Okay? Looking at this balanced chemical equation, we have 3 moles of silver chloride, so that's going to go on the bottom, and that's from 1 mole of chromic chloride. So again, we're getting those numbers from the balanced chemical equation. We'll make sure our units cancel, and then we can convert our moles of chromic chloride into grams of chromic chloride. And again, we'll use 1 mole equals the molar mass to do that. Since moles of chromic chloride has to cancel moles of chromic chloride down and to the right, 1 mole will go on the bottom, and the molar mass in grams will go on the top. We'll make sure our units cancel, and then multiply all the numbers on the top, divide by all the numbers on the bottom, and we'll get our answer. All right, we have one last type of problem I want to cover today, and that's our moles to molecules. Okay, this is very similar to what we've been doing, except instead of converting to grams using the molar mass, you're going to convert to molecules using Avogadro's number. So our key conversion here is that 1 mole is going to equal 6.022 times 10 to the 23rd molecules of whatever it is. Okay, so this says how many water molecules are produced when 0.010 moles of O2 react. So we're going to set this up just like we've done before. Okay, we're starting with our moles of oxygen. So the first thing we need to ask, can we convert compounds right now? Our answer is yes, right? Since we're starting in moles, we can go ahead and directly use the mole ratio right now. Okay, we're trying to find out information about water, so we'll use that mole ratio to convert from moles of oxygen to moles of water. So we're going to put 1 mole of O2 on the bottom from that balanced chemical equation, and we'll put 2 moles of water on the top, again using the numbers from the balanced chemical equation. So that's what we've been doing so far. Now comes the difference, okay? Instead of it asking, how many grams of water, this asks how many water molecules, okay? So now we're going to use Avogadro's number to do this conversion. So we'll put 1 mole of water on the bottom because we have 1 mole. And then we'll put 6.022 times 10 to the 23rd molecules of water on the top. Okay, so this is all the same process. The only difference here is instead of using the molar mass to convert moles to grams, we're using Avogadro's number to convert moles to molecules. Okay, once we're confident we've found what we're looking for, we can multiply all the numbers on the top, divide by all the numbers on the bottom, and we'll get our answer. Alrighty, go ahead and complete problems number 6 to 25 on the Chapter 11 lecture worksheet. And this is actually the end of today's lecture. Okay, we covered a whole new skill today. We learned how to use the mole ratio to do stoichiometry. Again, like I told you guys before, this, stoichiometry calculations are a foundational piece of chemistry. Chemistry uses stoichiometry all the time because chemistry is based on reactions. So in a chemical reaction, we always have a balanced chemical equation. And this stoichiometry allows us to convert, grams or moles of our starting material into grams or moles of our product. So stoichiometry is a very important calculation in chemistry, and we use this at all levels of chemistry, from the easiest chemistry course to the most difficult chemistry course. Everyone uses stoichiometry, and you'll see it show up in other classes as well. So really make sure you're really understanding this chapter. I would make sure to do every single practice problem and maybe do them twice. Make sure you really have a good grasp of how to do these calculations. And if you don't, please reach out so I can help you and clarify things. A lot of times it's one simple, easy thing that I might tell you that, just kind of makes this, aha moment. So make sure you reach out if you're in need of an aha moment. Otherwise, keep working hard, and I will talk to you guys next time.